Hi students, welcome to class. Lesson 7.7 is entitled Transforming Exponential and Logarithmic Functions, and the lesson will require a use of the graphing calculator. So if you don't have yours handy, please pause the video now and go and get it. Okay, now that we have our calculator all set, let's take a look at the learning goals. So our first learning goal for lesson 7.7 is to transform exponential and logarithmic functions. So that's what we've been studying in this chapter, the exponential functions and exponential growth and decline, and the logarithmic functions, which would be the inverses of those functions. And we'll be looking at transforming them by changing the parameters. So we'll start off the lesson reviewing all the rules for transformations, that we've been focusing on each time we look at a new family of functions. We'll be looking at the translations, the compressions and stretches, and of course the reflections. Our second learning goal is we're going to describe the effects of changes in the coefficients of exponents and logarithmic functions. So we'll be taking a look at if we change something in the function, what is going to happen to the graph. So we'll make some predictions about the shifts, whether it be slides, stretches or compressions, or reflections. Now you can see here listed, just to start the lesson, is all the transformation rules that we've been studying quite in depth throughout the entire course. So as we go through, we're going to go through an example of each one of these. So we'll review the rule at that time. But I just want to make one quick correction. I noticed down here on the reflection, if you'll kind of look right down here, right there, for the reflection over the y-axis, the x somehow got shifted down. So this should say, we'll be looking at like a basic example of 2 to the x as our parent function. So a reflection over the y-axis would occur if we raise 2 to the negative x power. So that's just missing the x. It ended up down here somewhere. So just write that in, and we're going to move to the calculator now. So if you'll follow along as we complete each of the examples, we'll be taking a look at each one of these rules in more depth through an example. Okay, so in today's video, we're going to be doing a little refresher of the transformation rules. And so we're going to be doing it within the context of looking at some exponential growth curves and doing some different transformations of it, just to kind of review those rules. So we're going to start off with something really basic. We'll just look at, say, 2 to the x power. So we know that that's exponential growth. We've been studying, growth and decay graphs, and so this is, I'm sure you anticipate what this is going to look like. And so remember, the characteristics of this graph are that as you read from left to right, it's increasing, and that's because the base is greater than 1, so it's exponential growth. The x-axis acts as an asymptote or a barrier that the graph will approach but never cross, and that's because we're raising positive 2 to different powers, and of course we're never going to get 0 from that because there's no number that we can raise 2 to get 0, and we'll also never get negative numbers. And so the characteristics of this graph are that it does have an asymptote at the x-axis, and as you're reading left to right, it is curving upward. So let's take a look first at the most basic transformation, and that's the vertical translation. So vertical translation, remember, occurs when we take the whole function f of x and we just add some k, some constant term to it. And so let's say we wanted to add, look at the example from the notes, and say we wanted to take 2 to the x, and we wanted to just add 3 to it. And we can probably anticipate what's going to happen. If we added 3 to the whole function, it should take the graph and slide it up 3. So let's take a look and see if that's what happens. Okay, so there you go, and it did exactly what we thought was going to happen. So taking the function and just adding on a constant will slide it up or down. In this case, it slid it up because we added positive 3. And so notice also what's happening is instead of the x-axis being that asymptote, it's like the asymptote, even though it's not technically part of the graph, came with it when it slid. And so now that new asymptote is at positive 3, or y equals 3. And the reason why that is because, that if you took that x-axis and slid it up 3, you'd be there at y equals 3. And so all of the points on this graph as you move to the left will approach 3 but never actually get there or never get below 3. So that's the vertical translation, and so we achieve that by taking the whole function and just adding some constant term. So what about horizontal translation? So horizontal translation, remember anything that's specifically a horizontal transformation will directly change x. So wherever x is, and in our particular function, x is the exponent, if we change it directly, we go right to it and make a change to it. And you also may remember that it, especially with slides, it sort of changes it in a way that's kind of contrary to what we might think. And so sometimes we'll say x lies to you. So if I were to take this x that's in the exponent, I take the 2 to the x, and I were to subtract 3 from it. So if I subtracted 3 from it, let's see what happens. So, and if you don't have the update on the calculator, be sure to put x minus 3, if you're following along, hopefully you are, that you put x minus 3 in parentheses as your exponent so that it takes that into account that it's the whole exponent. Otherwise, if you don't and you don't have the update, it might almost treat it like it's a vertical slide down 3, okay? Because we want to say we're actually subtracting 3 directly from the x. So hit graph, and you'll see that, in fact, it has moved the graph 3 to the right. Now, that might be surprising, but if you remember all the things we've studied about horizontal translations, and it's sort of the opposite of what we think, because it's you're subtracting the slide amount from x. So if you're subtracting a positive 3, it stays minus 3. If you're subtracting a negative 3, which would indicate a left slide, it actually turns into plus 3. So it looks a little funny in the equation itself, but you just kind of have to remember that the slide horizontally is sort of the opposite of what we think. Now notice the asymptote did not change here. Okay, it took it a little longer to get to that point, but I mean it is still hugging the x-axis, and so we still say that the x-axis is the asymptote, and that didn't affect it at all. So a vertical slide affected the asymptote, but the horizontal one didn't. Okay, so since we've covered the slides, left or right, up or down, let's move on and talk about stretches and compressions. So first let's look at the most basic type, which is the vertical stretch or compression. And you may remember that a vertical stretch or compression is achieved just by taking the whole function and multiplying by some constant value. So if we multiplied by some constant that is greater than 1, we would do a vertical stretch. So we're stretching things vertically, which means the graph would kind of get pulled away from the x-axis, sliding it or stretching it up or down. And so to do that, we would have to multiply by something greater than 1. So let's take a look at maybe the one that's in the study guide, 6 times 2 to the x power. So we're taking this basic parent graph and just multiplying it by 6. So we'd anticipate it would stretch it quite a bit, and it should make it much taller and further away from the x-axis. So let's see if we graph that, see what that looks like. There's the original, and clearly there's the stretch. And so now notice when we did this vertical stretch, it really did nothing to the asymptote. It is still coming down, and eventually, so you can see here, it's coming down, and it is kind of eventually getting to the same spot where the original graph is, and it's hugging that x-axis. So it's never going to cross it because it's still taking positive 2, raising it to different powers, but then multiplying it by 6. So there's no way you could ever get a negative, or no way you could ever get 0. So that's a vertical stretch or compression. If I had multiplied instead by something that would be less than 1, so let's say we, instead of 6, we put in, say, 0.5 or half. So we put 0.5 in, and we hit graph, you'd see that this would be a vertical compression. So that's going to flatten it down. But again, no change in the asymptote, but just pushed it down closer back towards the x-axis. So the points are only half as far away from the x-axis as they were to begin with. So what about horizontal stretch or compression? Now the horizontal stretch or compressions, you may remember, are very tricky because first of all, you have to change the x directly. So we're going to have to go up into the exponent to change it, and I'm going to group this in parentheses here. And so if I wanted to say, for instance, multiply the exponent by 1/5. If I multiplied by 1/5, what that's actually going to do is horizontally stretch it, because remember that the scale factor that we multiply by is always the reciprocal of whatever we want. You know, if we want to stretch it by a factor of 5, we'd actually multiply by 1/5. So horizontal transformations in every way are really kind of tricky, but you know, so in the case of slides, if you add 3, it's actually moving it left. While in the case of horizontal stretches or compressions, if you multiply by 1/5, it's actually going to stretch it. So let's go ahead and do that. Let's multiply by 1/5. And so just to be safe, we're going to put another set of parentheses to put our fraction in. Okay. And then multiply by x. So what this is going to do is just multiply the x, which is the exponent, by 1/5, and then it's going to raise 2 to that power. Let's take a look and see what happens. Okay, so clearly you can see that horizontal stretch. I mean, look at how far away the points are. Like, you know, you can barely even see the curve of this graph because it's stretched so much. So that's a horizontal stretch of factor 5, but to accomplish that, we had to multiply by 1/5. And so that, I guess if you went back and you looked now, and instead we multiplied by 5 instead of 1/5, you'd think it would compress it horizontally, right? Let's see, and let's see what that happens. I'm going to delete some of this stuff out. Okay, so now make it 5x for the exponent instead, and you'll see, sure enough, it compresses it, there you go, horizontally, excuse me, so it's pushing it back in towards the y-axis. But notice in neither one of these cases did the asymptote change, so the x-axis is still the asymptote. Okay, so our final category of transformations is, of course, the reflections. And so to do a reflection, we're going to look at both over the x-axis and over the y-axis. So the most basic one, the one we've seen probably most often, is over the x-axis. And so when you want to reflect a function over the x-axis, you simply have to take the opposite of the entire function. And for something like 2 to the x power, that just means sort of just putting a negative out in front, because that's the whole function is 2 to the x, so you take the opposite of the function. And so let's take a look at what that would look like. So opposite of 2 to the x power, and that should reflect it in a way that's vertical. So a vertical reflection would actually go over the x-axis, because it's, instead of the graph facing up, we're going to anticipate if it goes over the x-axis, it should face down, which means it's changing its position vertically. So let's take a look at what that would do to the graph. So sure enough, it just took the graph, reflected over the x-axis. Now notice that the asymptote is still the x-axis. It's just that the graph is approaching it now from below instead of above. So what about reflection over the y-axis? How are we going to accomplish that? So what would we have to do to the function? Well, to reflect over the y-axis, we're going to be doing a horizontal reflection, right? Because we're going to be moving the graph in a position horizontally. And so remember, to do any kind of horizontal transformations, you have to go directly to the variable x and change it. So here x is in the position of the exponent. So if I just took the opposites of, and in fact maybe just to be safe in case you don't have the update, let's put this in parentheses, took the opposite of x, then that should reflect that right over the y-axis. Let's see if it does that. So sure enough, it took that exponential growth curve, and by reflecting it over the y-axis, it made it look like exponential decline. Notice the x-axis is still the asymptote. It just took all the points, and it just flipped them over the y-axis. Okay, so it's time to look at a few examples. Now that we've focused on each one of the different transformations, let's see if we can look at some transformed functions and describe the things that are occurring based on the equation. Example 1 shows a graph of two functions, f of x and g of of x. And we're told that g of x's equation is 2 to the negative x plus 1. And the question asks us to tell how the graph is transformed from the graph of the function 2 to the x. So f of x, the blue graph here, is 2 to the x power. Now if you look at the graph, it looks like the graph had to have been reflected because g is facing the other way. You can see that it's, instead of looking like exponential growth, it now looks like exponential decline. But also notice that here where the graph is approaching that x-axis, which we know is called the asymptote. Now if you look at the other graph, it is actually approaching a line a little higher than that. It's actually up 1 from that. So if we look at that equation, this 2 to the negative x plus 1, I think you can see where those things become the reflection happens right here. And we took the opposite of x. So when we directly change the x, it causes some sort of horizontal transformation. And that's exactly what happened to this graph. There was a horizontal reflection, which means a reflection over the y-axis. So we would say the transformation is a reflection over the y-axis. But then also this plus 1 off the end here, what that's doing, remember, is that's sliding it up 1. That's a vertical translation, and in this case, the plus 1 means it's moving it up 1. So our description of this would be a reflection over the y-axis and a vertical translation up 1. Now notice with that red graph, as we said, it's not approaching now the x-axis as its asymptote. Instead, it's approaching that line there at 1. It's like we have this imaginary boundary here at 1 that this is never going to cross. And so we would say that our asymptote is y is equal to 1. And that, of course, coincides with that shift up 1. Let's go ahead and turn the page. Okay, let's see what's going on in example 1. And I want you to try this one as a you try question. So you know the drill. That means pause the video now and complete the question, tune back in, and we'll check to see how you did. So go ahead and pause the video now and tell how the graph was transformed from the parent function 2 to the x power. Okay, so as you looked at the change from 2 to the x to the new function 2 to the x minus 2, you can see that what they did is just subtracted 2 from the exponent x. And we know that when we change directly the x in the function, that's going to be some sort of horizontal transformation. And in this case, and because x lies to you, in this case the slide was 2 to the right. Even though it said x minus 2, we know that in the case of x transformations, they're not always as they seem. They're not always as straightforward as the y transformations or vertical transformations are. So this is a horizontal slide 2 units to the right, and you can actually see all the points sliding to the right. Well, what that means is because it was just slid left or right, the asymptote doesn't change at all. And so in this case, it's still the x-axis or the line y equals 0. Okay, how about example 2? This time we're asked to describe how the graph is transformed from the graph of its parent function. So if we were to look at g of x is equal to 2/3 times 1.5 to the x power. When we say the parent function, this is what we mean. It's just the base without any changes made to it. No coefficients, no changes to the exponent, no negatives out in front or anything. It's just the basic function. And so that is the f of x that we see there, the blue graph. The change that was made, the only difference between these two is this 2/3 that's out in front. And from the transformation rules, we know that if you just multiply the whole function by some number between 0 and 1, that's going to cause us to do a vertical compression of the graph. So that's why you can see that graph just getting closer into the x-axis. You can see that the red graph, or in my, you can't see it on yours, but in mine it's red. It's just compressed. It's pushed back down towards the x-axis, and that's because it's being pushed from either side, compressed down. Now the y-intercept. Well, when we say the y-intercept, that means when we put in a 0 for x, because on the y-axis the x value would be 0. So that's usually how we find a y-intercept. Well, we know that anything raised to the 0 power except for 0 is 1, and so this part of it is equal to 1, and then 2/3 times 1 is 2/3. So the y-intercept would be 2/3. Now, as far as the asymptote goes, you can see that the compression in this case did not do anything to the asymptote. It is still just approaching the x-axis, or y equals 0. So you can say it either way, x-axis or y equals 0, and that is still the asymptote. So now that we've tried another one together, let's give you an opportunity. We're going to do another you try question. So we'll designate B as a YTQ, and I'm going to have you pause the video and give this one a try. Now notice there's a little caution down here, so read that carefully before you complete and fill in the blanks here for this question. So I want you to pause the video now and try example B. Okay, so that you try question was a little bit tricky. That's why I included the caution in the notes, because anytime we combine horizontal transformations, in general, horizontal transformations are always the trickiest. They really are kind of counterintuitive. And so I showed you here that what that negative x plus 1, because it's all in the position of the exponent, really means is that we took the opposite of x minus 1. Well, x minus 1 in the position of the exponent would actually move 1 to the right. But then putting the negative out in front, that actually changes the sign on the x to negative and the sign on the negative 1 to positive. So this really is a slide 1 to the right. It's normally x is lying to us, so now it actually looks like x is telling the truth, that it really is moving 1 to the right. So you can see clearly that this graph was reflected over, which would look like this green graph here, and then it was slid to the right. So after the reflection, then it was slid to the right, and that's where it ended up in its final position here at h of x. Oops. Now, of course, the asymptote doesn't change at all. It's still the x-axis in this case. On our exponential graphs, the only thing that's going to change the asymptote is going to be a slide up or down. And then the y-intercept, you can see that this graph is crossing at e, or e to the first power, because right over here, when we put in 0 for x, it simplifies down to e to the first. Okay, let's turn the page. Let's go ahead and do this one together. So our function is g of x is equal to 2 times 2 to the negative x. So let's take a look at each piece of this graph transformation. So the 2 out in front, if we think about that parent graph, which is 2 to the x power, how it's been changed is there's that 2 out in front. Well, remember that that part is a vertical stretch, multiplying by something greater than 1. The whole function by that causes a vertical stretch. And that negative in front of the x there in the exponent, we know that that is actually going to cause, because it's changing the x directly, some sort of horizontal and reflection. And when we reflect horizontally, that means we're actually flipping over the y-axis. Our description would be a vertical stretch by a factor of 2 and a reflection over the y-axis. And clearly you can kind of see that that's been happening, because the reflection would have put the graph here. And then you can see how then it was stretched and pulled up away from the x-axis, so it's stretching it up. And I did just notice also that these labels are flip-flopped. I just noticed that. This blue one should have been labeled as f of x, and the red one is g of x, and you can see that they were labeled correctly, the little small letters. So this one actually should have been your g of x, and this one is right here, your f of x. Okay, so in this next segment, we're going to take a look at how these transformation rules affect the logarithmic functions. So we've looked at the graphs of exponential growth and the transformations of exponential growth. And so now it's time to move on and look at the inverse function to exponential functions, and that's the logarithmic functions. And so we're going to take a look and explore some transformations of the log function. And remember, our calculator is kind of limited to doing log base 10 and natural log. So we're going to be looking at some examples of base 10 logarithms. So, you know, we can graph a log function on our calculator. It's just going to be log base 10. So if we hit log and x, and we look at that's going to be our basic parent graph. And this is what the log of x would look like. That's what the graph. And you know, it's kind of hard to see that, but you know, maybe if we change the window just a little bit. So I'm going to just play around with the window just a second. So if we say take the window and then say we change it so that maybe that we don't have such a high max for the y, so we're going to maybe not go down quite as far or up quite as far, so maybe go to just down to -5 and up to +5. We might be able to see this graph a little better. And hit the graph again. Well, it's a little better. You can see it. But now that graph, you can see what it does is it comes down and it hugs the y-axis. So the y-axis is the asymptote. And then it kind of just rises from the y-axis and comes up and just curves over and will extend out and just keep kind of getting higher and higher, just marginally higher. And you can see if we went to the table and we looked, and you can see starting at 0 and below, I mean, that's error, and that's because the graph doesn't exist there because that y-axis is the asymptote. But as you kind of move forward on the table, you'll see the values get bigger and bigger, and they actually do continue to grow, but it's just very slowly. And that's because, remember now, we're talking about the value of the function is the exponent. So the exponent that you're raising 10 to. And so obviously those values would take till you got to 100 for it to be 2 for the output, because 10 to the second is 100. So that's what the graph of the log of x looks like. So we're going to take a look first at a vertical translation. So we're going to slide. So if we took this graph, log of x, and we just added onto it, say we added 2. So let's add, we'll go ahead and do with the one that's in the notes. We'll add 3 to it. So if we hit graph, we'll just take that graph and move it up 3. Notice the y-axis is still the asymptote. It's just it moved it up 3. So all the points are just 3 more away from the x-axis than they were before. And you can see this here in the table that each one of these y sub 2 values is 3 higher than the original, which was for the log of x. So if instead we subtracted, say we went down here and changed this to -6, and we might not actually see it because the way I changed the window, but it's going to take that graph, and yeah, you can't see it. You can kind of see it just started the graph a little bit. If I change the window, maybe went down to -10, you'd be able to see it then. Change in window just sort of blocked that spot out. So now you can see it moved down 6 units. So, but in each case, the asymptote, which is a vertical asymptote this time, it did not change. It's still the y-axis. So what about if we wanted to make a horizontal slide? So remember that horizontal slides have to go and change the x directly. So if I were to take out this parenthesis and now group the change right there with the x, and let's only make it 2 so we can make sure we still see it on the screen. So if I took 2 away from the x, if we kind of think about what we know about horizontal slides, you might think that this would move it 2 to the left, but we know that it actually should move it 2 to the right. And so let's see what happens. And sure enough, it moved it 2 to the right. And so now the asymptote, instead of being the y-axis, actually turns out to be that line x equals 2. And you can see that. See here on the table where it started, the value is an error there at 2, and then for all values below it. And that's because, when it used to be at 0. So it actually moved that vertical asymptote 2 to the right. So the log graph's asymptote will change when we do horizontal slides. And that's because it actually has a vertical asymptote. So that asymptote will actually kind of slide along with it. So if we move the graph to the right, 2 as we did here, the asymptote moves 2 to the right. If we had moved it to the left, the asymptote would move to the left along with it. So again, in this case, directly changing the x, meaning, which is grouped with the log, grouping it there with the x and changing it directly by adding or subtracting will slide it horizontally, left or right. Okay, so how about vertical and horizontal stretches and compressions? So as usual with a vertical stretch or compression, we take the entire function and we multiply by some constant term. So let's say we wanted to stretch this by a factor of 6, as the one in our study guide or guided notes indicates. So if we multiply the log of x by 6, so it'd be 6 times the log of x, then we would expect that it would stretch this vertically by a factor of 6. So let's take a look and see what that looks like. And just to be safe, to make sure we can see it, I'm going to do a zoom standard. So if you're following along, I'm going to just zoom back to that standard window. And there's the original, and there's the vertical stretch. So all of those points are now just 6 times as far away. And if you actually looked at the table here, and you took each of these values and multiplied them by 6. So for instance, the 0.30103, which is the value for log of x at when x is 2, then the new value with this vertical stretched function would be 1.8062, which you can clearly see is 6 times greater than that. So it's just taking all the y values and multiplying them by 6, which is in effect stretching it vertically away from the x-axis. Now if instead we put some number in front, like say 1/4, so if we wanted to come down here and insert a 1/4 instead, we're going to multiply by a 4th. We should anticipate that it was going to compress it vertically. So the log of x, we're multiplying by a 4th, and you can see what happens. So there's the graph. It's going to be really hard to see, but you can kind of see the line coming up there. Unless I change the window, it's really hard to see, but it's because the graph is so close to the x-axis because we just compressed it. So it's only a quarter of the way away from the x-axis as it was to begin with. And you can see these values here in the table reflect that. So especially this one at 4, you can see if, we had 0.60206, and if we multiplied that by a 4th, we'd get about 0.15, because 0.15 is a 4th of 0.6. So that would do a vertical compression. All right, so how about the horizontal stretch and compression? So remember, those are the interesting ones. They are a little tricky. So they require us to multiply x directly by something. So let's say I went in and I multiplied x directly by, say, 1/5. Okay? So 1/5, which is a number less than 1, and I'm multiplying x directly by it. Notice I'm keeping it all in parentheses with the x. So because it's horizontal, it's sort of the opposite of what we think is going to happen. If we're multiplying by a 5th, you might think it's going to compress it. But in fact, it actually is going to stretch it. It should stretch it by a factor of 5, which means it's going to pull it further away from the y-axis. We'll stretch it horizontally. Let's take a look and see what happens. And it's kind of hard to pick up on it because of the fact that these graphs are in general are kind of hard to even see in this window, just because of how we're talking about powers of 10. And so if we kind of zoomed in a little bit on that, let me see if I can zoom in and make this look a little better. I guess that probably does it a little better. You can see a little bit better how it's stretching it that way. It's really just 5 times as far away from the y-axis as it was before. So multiplying the x by 1/5 actually did a stretch by a factor of 5, because remember, you have to take the reciprocal of the scale factor when it's horizontal. So if instead I went in here into this graph and I changed this so that I multiplied by 3, that actually would do a horizontal compression of 1/3. So I'm going to take these out, and I'm going to multiply instead by, I don't need those extra parentheses, multiply by 3 instead, and see what happens. That should do a compression this time, should push it in towards. Again, it might not be that easy to see. You can kind of see a little bit better there, just because now you can see that little piece up around in here where it got pushed back towards the y-axis, so it was being compressed. And so now, of course, we have to look at reflections. So first, reflection over the x-axis, and the same rule applies no matter what the function is. If you put a negative out in front of the function, you take the opposite of the whole function, and the whole function is log of x. It should reflect it over the x-axis, and let's take a look. You'll see exactly what that does. And again, it's kind of hard to see closer to the origin there, but as you get further away, you can see that those branches just flipped over the x-axis. And finally, then to reflect over instead over the y-axis. Now we're going to take the opposite of the x directly. So now we go on where the x is, take the opposite of that, and that should reflect it over the y-axis. And then notice in each one of these cases, the transformations didn't affect the vertical asymptote except for when we did a horizontal slide. So, you know, the asymptote still is the y-axis here. It's just from the opposite side. It's coming from the negative side. And the only thing that really changed the log function's asymptote was when we slid it to the right or to the left. So a horizontal slide, and that's because it has a vertical asymptote. With the exponential growth curve, it had a horizontal asymptote, so the thing that would change that would be the vertical slide. So let's take a look at some examples of transforming log functions. We're asked to find the asymptote and describe how the graph is transformed from the graph of its parent function. So our new function g of x is 5 times the log of x minus 2. And that means that our parent function is log of x, and it's labeled here as f on the graph. So this graph, we know, typically in its standard form has the y-axis as its vertical asymptote. And so what's been done to this function to transform it in g of x? Well, there's been a 5 that's been multiplied out in front, and then subtracted 2. Now notice that it's not, the 2 is not grouped together like this with the x. Instead, there's not parentheses there, which means that that 2 is being subtracted off of 5 log of x. And that makes a big difference because remember, anything that was directly subtracted from x itself will cause a horizontal slide. But in this case, because it's subtracted from the whole function, you can see that this is actually sliding down 2, but then the 5 that's out in front, that's going to give us that vertical stretch. So this is a combination of a vertical stretch and a vertical slide down 2. But notice that the asymptote is still the y-axis, or x is equal to 0. There is no change there. It is still that y-axis that this graph is approaching but never crossing. Okay, so how about example 3b? Find the asymptote, describe how the graph is transformed from the graph of its parent function. Okay, so the parent function of the log of negative x plus 2, that's the new transform function, is of course the log of x, or natural log of x, excuse me, and it's represented as the blue graph here. So we know that that's, you know, looks just like the log function, but instead of the base being 10, the base is e. And so it still has the same characteristics, that now it has a vertical asymptote, which is the y-axis, or x equals 0. And so now we've been doing some transformations to it. We've done these things right here to change that. Instead of x, it's now opposite of x plus 2. Well, because that is all grouped with the x, we can tell those are both horizontal transformations. And anytime you layer horizontal transformations, it gets a little tricky. So I included this little caution here. So think about what this really means the natural log of the opposite of x minus 2. To get that plus 2, what actually has happened is we took the opposite of this whole thing, x minus 2. So that made the x negative, it made the negative 2 now a positive 2. So what's really actually going on, though, is still, if the minus 2 would slide it 2 to the right, and the negative out in front of the x would actually reflect over the y-axis. So you can see that that's actually what's happening here. So if we kind of showed that intermediate phase here where the reflection happened, it's like the graph reflected over, that's where the green graph is coming from. But then every one of the points just slid 2 units to the right. And so that definitely does describe what's going on here. So our description of the transformation would be a reflection over the y-axis and a slide 2 to the right. Now, as far as the asymptote goes, you can see here that this line is really approaching right about here, which is at 2. And so that makes sense because we did a horizontal slide 2 to the right, so that took the asymptote, which is a vertical line, and moved it to the right as well. And so our new asymptote is at x equals 2 instead of at x equals 0. Okay, now it's time to move on and take a look at our final learning goal, which is to write these transform functions. So let's turn the page. Okay, so in each one of these examples, we're going to be given a parent function and asked to do some specific transformations to the parent function. And to verify our function that we come up with, we're going to graph these on the graphing calculator, so you still want to have that handy. Example A says that our function is f of x equals 4 to the x. So we know this is an exponential growth function. Base is greater than 1, so it's growing. And this graph is going to be reflected across both axes. Okay, so we want to reflect across both axes, and then we want to move it 2 units down. So let's think about how we reflect. If we want to reflect over the x-axis, we can achieve that by putting a negative out in front of the function, so taking the opposite of the function. So if we started off with that, we'd have a negative out in front. To reflect over the y-axis, we have to take the opposite of the x. Well, the x is the exponent, so we take the opposite of x. And then to move 2 units down, we know we just subtract 2 from the whole function. And so opposite of 4 to the negative x minus 2 should do it. Well, to be sure, we're going to go ahead and graph these. I actually graphed them. And if you want to do that, go ahead and go along. I have a picture of what the graph looks like. So I'm going to graph the original parent function here, this. And then I'm going to graph our new function, and we're going to see if it did what it was supposed to do, which is reflect over both axes and move 2 units down. So here's a picture of the graph that I did. And you can see I just entered our function right there. And let's take a look at the two graphs. So the original graph is, of course, this graph right here. This is our original f of x. That's our exponential growth curve. And in order to get to this new graph, you can see that we would have had to reflect over both axes. There would be the reflection over the y-axis. Then you could see how we could reflect it then over the x-axis. So there would be the reflection over the x-axis, and then you can see the slide down too. So the intermediate graphs, they're the first reflection over the y-axis, then the reflection over the x-axis, and then you can see how the graph was just slid down. To give us our final position at opposite of 4 to the negative x minus 2. So the next example, the parent function, is the natural log of x. So this is our log function, and we're going to compress it horizontally by a factor of 1/2 and move 3 units to the left. Now here's just a little helpful hint on a caution, that when we do these layers of different horizontal transformation, you should always try to wait and do the horizontal stretch of compression last to get the full effect. And so let's take a look first at the slide. So if we wanted to slide 3 units to the left, we know that we have to go into the function and directly change x. So we go into the x, and it's the opposite of what we think. If we think 3 left, we might think, oh, we've got to subtract 3, but we know that x lies to you. So this would entail us having to go left. We'd actually have to add 3. But then we want to do this compression of a 1/2. But when it's horizontal, remember, we actually have to multiply by the reciprocal of the compression factor. So the reciprocal of 1/2 is 2. So what we'd have to do is kind of sneak in here in front of this a 2 that would actually do that compression horizontally. And so if we then were to see the full effect of that 2 is actually going to have to multiply by both the x and the 3 to give us a final function of ln of 2x plus 6. And just to make sure that that did what it was supposed to do, which is compress it by 1/2 and move it 3 units to the left, let's take a look at what the graph would look like. So I'm going to graph the original, and I'm going to graph our new one, and we're going to see if it did what it was supposed to do. So on my graph, what I did is I showed kind of just the different layers. I showed the compression horizontally in y sub 2, but ultimately the final graph we're looking for is this natural log of 2 times x plus 3 or 2x plus 6. And so if you look at the original graph, which is here in the blue, and the final graph, which is here in the red, you can see that it's a mild one, but it is a horizontal compression, compressed back in towards the y-axis, and then the slide 3 units to the left. So you can see that 3 units to the left has occurred. Even though it says 2x plus 6, it really is only moving it 3 units to the left. And we're going to go ahead and leave example C as a you try question. So please complete example C, and you can tune back in, and I'll put the graph up so you can see how you did. So pause the video now. All right, thanks for giving that one a try. So the correct answer for g of x that would accomplish both the vertical stretch by a factor of 2 and a translation 3 to the left would be 2 times log of x plus 3. Now it's really important that you have the x plus 3 in parentheses so that we're changing x directly and then taking the log of it. So because otherwise, if you don't have the parentheses, the plus 3 would actually cause the slide to go up 3. So to ensure that it's a horizontal slide, we have to make sure it's grouped specifically with the x. And you can see that the graph does depict that stretch vertically by 2. You can see that the new graph here is a little bit further away from the x-axis. It's been stretched vertically, and then of course it's been moved 3 units to the right, so you can see that slide going this way to the, 3 units to the left. So that does it for today's lesson. I'll see you in class.